All right. Hi, everybody. Thank you for joining our data science webinar. It is sponsored by ASA Statistics in Marketing section. If you are not a member of ASA Statistics in Marketing, please consider joining us as a member. ASA provides incredible resources about statistics and data science. You can go to scientistcafe.com for a link to our section. And you can also check more detail about the talk through the website. There are a list of our historical talks and recordings. If you are interested in any of those, you are more than welcome to check them out. If you participate in the live broadcasting, you can submit your question using the chat function on YouTube. Today we have Professor Max Zhu talk about his research on product design. Max is an assistant professor of marketing at University of California, Riverside. If you check our website before, you may find that he changed job. And his research interests include advertising effectiveness, pricing, and product design using quantitative modeling methods. Without further ado, I will turn it to Max. No. Can everyone see Max now? I think people see you.
Okay. Hello. Thanks for joining us today. And thanks for a nice introduction, Hui. Well, as Hui introduced, my name is Max Zhu. I'm assistant professor of marketing at University of California, Riverside. Then let me first share my screen so that you can see my presentation slides. Okay, so today's presentation is about a statistical method, how we can design an optimal visual design of product or a product package, especially when there are a lot of attribute levels. So if there are lots of attribute levels for each attribute, and then the big problem is that there are a lot of combinations which are candidate design profiles that you have before you run an experiment.
Max, sorry, we don't see your presentation. We don't see the slide.
You still see my face?
Now it works. Can you do that again? Just full screen.
Just a second.
Cool.
I'm going to share my entire screen instead.
Okay.
And then
that work.
Can you see presentation slides?
Yeah.
Okay, thank you. Okay, so when you have a lot of attribute levels for each attribute, and the biggest problem is that you will have a lot of candidate design profiles. So in traditional experimental methods, it is impossible to test all those possible combinations. So typical problem that practitioners face in this domain is often called Frankenstein problem, where you find the best level of attribute for each attribute, and then if you combine together, and then the final outcome doesn't look really good. So that means each attribute is very strong. However, the combinatorial effects are ignored. So putting those together doesn't give you synergy, and then that is actually, that sometimes gives you negative synergy. So in order to avoid it, you will need to find which combination is the best, and then this is not obvious problem. So in this project, we try to resolve that issue, proposing a new statistical method. Okay, and I already talked to Hui, but I wanted to make it as interactive as possible. So if you have any questions in the meantime, just please let Hui know, and she will tell me any questions that you have, and you can interrupt me at any time. So if we consider a design problem, and then there are typically a few attributes. For example, there could be a color of lid and color of bottle and color of brand name. And then in the center, you might have some graphics in it. And even though you have only a few attributes, typically you have a large number of levels as a candidate for each attribute. So for example, you might have 10 colors for lid in your mind and 10 colors for bottle in your mind, and such things. Then the number of attribute levels would be large in this design problem. And well, this is a famous design experiment by Google. So they run extensive design experiment to figure out like which is the best design for their logo. And at a glance, this is a very simple problem. So only 6 letters, and then you will need to figure out the color of each letter. However, in Google's experiment, they tested 41 different blues, and this already gives you 41 variables in the design metrics because you cannot code that as continuous RGB variable to measure consumers' preferences. And not only that, you will need to also test 41 different red, and then the number of variables would be 41 plus 41. However, the number of cases of all combinations would be 41 multiplied by 41. So the number of explanatory variables or number of regressors here would be a lot already. However, the more serious problem is that there are a huge number of combinations which are candidate profiles in your experiment, so it is almost impossible to test all of them. So for example, if you have like 10 candidate colors for each letter, and then the number of candidate profiles that you have would be 10 to 6, which is a million. And then in a design experiment, you cannot ask the subjects to rank order the whole 1 million design profiles. So you will need to handpick small number of design profiles, and then you will need to run an experiment. And in this process, it is often omitted to include important combinatorial effects that you wanted to test. So the definition of optimal design is very obvious. So you want to find the most preferred combination of different attribute levels. However, because of this large number of combinations, you cannot test all those combinations directly to the subjects. So in the traditional experimental methods, what you typically find is a combination of the most preferred attribute levels. That means you can find, so in this camera example, you can find the best lens, you can find the best screen, and you can find the best shape. However, it is possible that when you put them together, the final outcome might not be preferred by consumers. This picture is actually not a camera. This is actually a cell phone that was introduced by Samsung a long time ago. And then each attribute is very, very strong for this product. However, putting together, this doesn't look like a cell phone, and then this wasn't accepted by the market very well. So this is the Frankenstein problem that I mentioned. So when you have a beautiful lens and beautiful screen and beautiful other features, but when you put together and then as a whole, the product is not the most preferred combination to the customers, then your design experiment didn't find the optimal outcome. So in this case, you can easily find the suboptimal outcome instead of the optimal design. So our goal is to overcome this Frankenstein problem. And there are several challenges to resolve this problem. So in typical design experiments, you can only test a small subset of all possible design profiles because you cannot ask to rank order like 1 million design profiles by your subjects. Therefore, the first thing that you have to do is with partial set of design profiles, you will need to learn consumers or subjects' preferences. And then, based on the partial knowledge of preferences, you will need to choose which combinations to be tested in the next round. Then, by doing that, you can more efficiently allocate your research, your experimental resources in a limited set of subjects and to a limited set of questions. However, the big problem is that it's not a very obvious problem. So you want to learn preference and you want to find a combination that will turn out to be the best in the next round. But that's not an easy question because you never know whether a certain combination would be better than the other combination unless you actually show that to the subject. So for example, in the first round, if you tested red-yellow combination, and then you want to know whether red-yellow combination is better than red-blue combination, then unless you directly test both red-yellow combination and red-blue combination, then it is impossible to know which one is better. So these combinatorial effects should be selected and tested in the future round, subsequent round of experiment. However, knowing which one is more promising is not a very easy question. And also, considering these combinatorial effects, like interaction effects, the dimensionality would be very high. So there would be lots of variables and lots of combinations. So it is very difficult to figure out which combination that you want to test in the next round of experiment. So we first try to review the existing experimental method to see if there's any extent method to resolve this problem. And typical machine learning methods to resolve this type of high dimensionality using adaptive experiment typically go for the combinations with fewer knowledge. So that means if you run the first round of experiment, and then if you run the model on the partial data, and then these machine learning methods would suggest the combinations with higher variance of preference parameters. That means if you have higher variance of preference parameters, that means you know less about this attribute level on the consumer's preferences. So this is actually maximizing the learning from a researcher's perspective. However, let's say there is a yellow color for the first attribute and red color for this first attribute, and then yellow is highly preferred, but variance is low, and red is low shows low red shows low preference, however variance is high, and then the existing method would prefer to test red instead of yellow. So it is possible that limited experimental resources are allocated to low preference region. So in this type of design experiment, the main goal is to find the best performing design, which is maximizing your expected market share when you introduce the product on the market. So maximizing learning of the entire preference region is not very important for this class of problem. And then what we want to do is try to know better in the high preference region to find out the best performing design profile on the market.
Next, when you
Yes.
say high preference, that's a mean value, is that right?
Yes, right.
So when you say high variance means there could be some people very like red, and some people very like dislike red.
Right, right.
That's what I mean variance. Okay. How the data looks like? Is that is that 1 to 5 score?
No, we ran in this project. We ran a choice experiment, and we estimated a choice model, and then we inferred a preference distribution out of consumers' choices.
Okay, so it's not a survey like what do you want?
No, no, it was choice experiment. That was a good question. Thank you. So we decided to propose something else. First of all, we wanted to make it consistent with, the question selection criterion to be consistent with the goal function of the experiment. So what we proposed is an aggregate level experiment, and then we wanted to propose a set of design profiles to be tested that are highly likely to be best performing design at the market level. So instead of running individual level experiment, we run aggregate level experiment. So that means, let's say you hired 100 subjects for your experiment, and then we ask exactly same questions to 100 people, and then we measure the market share out of those 100 people. In doing so, we can measure the market share with high stability instead of choices choices that are subject to individual level choice errors. That means the inference of interaction variables or interaction effects or synergetic effects are also more stable than the individual level estimation. And we focus on the expected improvement at the market level performance. So after running the first round of experiment, we have partial knowledge of consumer preferences. And then based on those preference parameters, we predict the expected market performance of the candidates that are not tested in the first round. And then we set up the criterion based on how each candidate would make improvement on the market performance relative to the best outcome we found in the first round. So the potential benefits that we expected are that the experimental resources are allocated to profiles that present high potential instead of high variance or high uncertainty. So we don't need to allocate our experimental resources to the low preference region. So this naturally balances between exploration and exploitation because we focus on expected improvement, which is a variance of high preference area. And we also evaluate or estimate combinatorial effects or synergetic effects at the market level performance. So the combinatorial effects present much more stability than individual level estimation. Conceptually, our proposed criterion directly operationalizes the market share maximization, and it balances between exploration and exploitation without random exploration that requires also some waste of experimental resources. Okay, then let me visualize our experiment. So let's just to say we have a design problem for the 6 letters, the simple case. And then let's just assume that we have 10 different colors for each letter. Then the design matrix would show very high dimensionality. That means the number of candidates, the number of data points would be 1 million, which is 10 to the 6. And the number of explanatory variables would be 10 multiplied by 6 plus two-way interaction effects. So even when we consider only two-way interactive effects, we already have 1,500 variables for this type of problem. So this is already a very large problem, but the biggest problem is the number of candidates, not the number of explanatory variables. So for the aggregate level experiment, we first set a common outside option across different questions to stabilize market share measurement. And this common outside option can be either a vanilla design or the current design profile on the market. Then subjects would evaluate their preferences relative to this vanilla design or current design on the market. Then in the first round, we don't know anything. We don't have any prior knowledge. So we can randomly choose like 3 other design profiles to be compared, or we can apply a partial set of traditional experimental criterion like de-optimality. Then with these 4 design profiles, the typical question can be asked, like, what is your favorite design concept? And then all subjects would get the same question, and then they would make a decision of like which one they liked. And then we can measure the market share out of the whole number of subjects. And then with the market share, we can estimate a choice model to infer consumers' preference distribution of each attribute level. And then with this estimated beta on the partial data set, we can choose the next set of design profiles for the second question. So the question is like, which candidates should be selected for the next question? And then as I summarized in the motivation, this is not a very easy question. So this is our research question here. So because we estimate, so in the first round, with a partial set of the data, we estimated consumers' preferences, which is posterior distribution of beta. So with this beta, we can formulate the predictive market share distribution of design profiles that are not tested in the first round. So this design, for this design profile, we can formulate a distribution of predictive market share. And there are 2 existing experimental criteria. So the first one is learning, which is typical machine learning type of method. So that learning type of method focus on exploration of design profiles with large variance. So by going for the size of this variance, you would focus on exploration. So in doing so, what you can expect is that you can learn more of overall preferences over all 1 million design profiles. However, as I said, if you go for that route, it is possible that you can also learn a lot about the design profiles that are obviously in the low preference region. And another existing method is exploitation, so which is similar to the recommendation system in the machine learning literature as well. So if you focus on exploitation, that means you focus on the mean performance. And if you focus on the mean performance, that means you get the mean from the previous round, and then you focus on the high performing combinations that you found in the first round. So it is basically reiteration of your finding in the first round. So let's say if you omitted all the important combinations in the first round, and then if you go for exploitation, it is possible that you got stuck on local maxima, or you just reiterate the best finding in the first round over and over. So it requires some random exploration to get out from the local maxima. So in order to overcome these limitations, we wanted to introduce new experimental criterion, which focuses on expected improvement. So we start from the same expected distribution of market share. And then on this distribution, we condition on the observed market share of the best design in the first round. So we know the market share value of the best design profile that we found in the first round. And if you take a look at this distribution, and let's say in the next round, if the new design profile turn out to be in the left-hand side of this distribution, that means we still keep the best design in the first round as the best one. So in this part, we don't really need to consider because we already have the best design in the first round. So the left-hand side variance does not give you the reason to move on to the second round. And if you find a design profile that gives very high variance in this region, and then that means you'd better to keep the best design in the first round. And on the other hand, the variance on the right-hand side of the best market share in the first round would summarize the probability that the new design profile would be better than the design profile that you found in the first round. So we wanted to focus on this upper tail expectation and upper tail variance because it's how promising the new design profile is relative to the best design profile that we found in the previous round. So conceptually, it summarizes, the upper tail expectation summarizes expected improvement relative to the best design profile that we found so far. So this upper tail integration would summarize the expected return of running the next round of the experiment. So this value would summarize whether running one more round of experiment is valuable for you or not. So we calculate this expected improvement for all design profiles that are not tested so far. And then we prioritize the design profiles with this high value of expected improvement. So we rank order design profiles in a descending order of this expected improvement. Then we show the more promising ones. That means higher value of expected improvement for the first question. And then for the next question, there would be the next set of design profiles. And our model specification is flexible. So our design criteria are not tied to any specific functional form. So in this project, we used a linear utility specification, however, with the normal distribution of error term. And we also used the two-way interaction terms in the utility specification. However, if you have a dimensionality or if you have a context that requires more complicated functional form, like higher order interactions or the error term with distributed with something else than normal distribution, you can easily combine those in this method. And theoretically, our expected improvement criterion is justified as the best route to find the most promising R&D project. So, so by going for the upper tail variance, that means we are looking for high risk, high return project for the next round of experiment. And then it has been theoretically shown to be optimal path to find out the R&D project with highest rewarding would be found in a shortest route by going for high risk, high return R&D project. with priority. And in engineering and statistics literature, this expected improvement criterion is justified as one step ahead optimality. So that means this upper tail expectation does not summarize optimality. However, it summarizes which one will be highly likely to be optimal after running in the next round of experiment. So it is called as one step ahead optimality, which is good for choosing the observations for the next round of testing. And it is also shown to balance between exploitation of high performance region and exploration of high potential, because it uses variance. However, it focuses on the upper range or high preference range of variance. So it doesn't require random exploration, and then it naturally, this single criterion naturally balances between exploitation and exploration. And for the empirical remedy of the large number of explanatory variables, we use Bayesian variable selection method. For the variable that is the preference parameter that is likely to be 0, and then we impose a very narrow prior distribution around the 0, and then that can easily shut down the parameters to be irrelevant. So this is our empirical suggestion. So we don't argue that this is the way that you should go for. However, in our context or in our simulation studies, we found some efficiency gain relative to lasso regression or just regular linear regression. So in order to see if our proposed expected improvement criterion works to predict the best performing design profile, we ran a simulated experiment. So in a the good thing of running this simulated experiment is that we assume that there are some preference parameters and there is a rank order of all design profiles, and then we run the model and then see whether the model predicted the best performing outcome, because we know which is the best performing outcome in the simulated world. In the experimental setup, we used the similar dimensionality that our collaborating firm wanted to test. So we had 4 attributes in the simulated product, and then each attribute has about from 5 to 12 levels of attribute levels. By doing that, we have over 5,000 candidate profiles in total, and then we have 32 main effect variables and 369 two-way interaction effect variables. And we assumed that there are 100 respondents, which is the number of respondents is a cost driver for the company. So we assumed a reasonable number of respondents here. And in the survey, we assumed that we ask 25 questions per each round. And then each question would show 4 different design profiles. And then we run the 5 rounds of adaptive experiments. So that means in the first round, we show the random set of 25 questions. And then based on the market share that we collected in the first round, we estimate the preference parameters, and then we calculate our expected improvement criterion, and then we choose the next 25 questions for the second round, and then we repeat that until the end of 5 rounds. And we generated the data based on the individual level choice. So we simulated as if the individual subject actually make choices based on the assumed preference parameters. And in the simulated data set, there exists substantive heterogeneity across different individuals. Okay, and after running 5 rounds of experiments, we tested the predictive performance of our method. So the solid line represents the utility regret, which is the difference between the true utility of true best design profile and true utility of predicted best design profile by our method. So that means if utility regret is 0, that means we predicted the best design profile, true best design profile based on our prediction. So after first round, so with only partial knowledge, the utility regret was about 0.7. However, after running all 5 rounds of experiment, and then we could predict the true best design profile after running the 5 rounds of experiment. And then even after 5 rounds of experiment, we only test 500 design profiles. So considering over 5,000 design profiles in total, we tested only less than 10% of design profiles. And the dotted line and dashed line present in-sample correlation of market share and out-of-sample correlation of market shares between true market share and predicted market share. And then both in-sample fit and out-of-sample fit are very high after 5 rounds of experiment, even after testing, well, like with testing only 10% of design profiles. And excuse me. And actually, number of respondents will be the cost driver of the firm's experimental resources. So we wanted to test whether we really need 100 people for our experiment. So we reduced the number of respondents from 100 to 50 and to 25 and to 10, and see how predictive performance would change in the simulated world. So what we found is with 100 respondents, 50 respondents and 25 respondents, we could still find the best performing design profile after running 5 rounds of experiment. But with 10 respondents per round, our results became rather unstable. However, 25 people is much lower than typical number of respondents in design experiments. So we think this is evidence of stability of our experimental method. Excuse me. And we also wanted to test how sensitive it is to the number of questions. So that means number of design profiles shown or tested to the subject. And we could still find the best performing design with only 20 questions per round. And it became a little bit unstable with 15 questions and 10 questions per round. And with 20 questions, actually, we tested only 400 profiles out of 5,000 profiles. And considering over 400 explanatory variables, with 20 questions, we have smaller number of observations than the number of variables in the design matrix. So even under that case, we could find the best performing design profile with the proposed method. And after running our method to the simulated experiment, we wanted to apply the proposed method to actual R&D project. So we worked with the largest CPG manufacturer in the United States, and we worked for a package design of the CPG good. So we ran an online choice-based conjoint experiment, and we showed high-resolution picture of the package. And we had about 450 respondents from United States and United Kingdom, and we split them into 5 different groups. And we ran the same aggregate level sequential experiments, and we ran 5 rounds of experiments. And in each round, we had 23 questions per round. And we are not allowed to show the actual picture of the product. However, the diagram that I show here can give you some idea of like how the nature of design experiment looks like. So the common brand name was not part of our experiment. The common brand name is there. And then we tested 4 different attributes. So the first one is visual illustration, basically a picture of the product. And we also tested different sub-brand names and material names and claim statements. So there are 4 attributes and well, around 8 to 10 levels for each attribute. So it's very similar to the dimensionality of our simulated experiment.
If you want to implement that experiment, do you need to calculate that real time? Like after the first round, you're gonna do you build a system that calculate and give the second round suggestion.
Well, that's a very good point. So so I will explain more in the later part of the presentation. However, the biggest benefit that I think of using this type of method is that we don't require real-time update.
Okay.
So this is aggregate level experiment. So it doesn't need to be question by question update.
All right.
So we can collect the data from a set of questions across different people, and then we calculate the market share, and then we choose the next set of questions. So it is not at the individual level. Everybody gets the same question. So the update can be at the end of the questions of each round.
Okay.
So we run the first round of experiment, and then update only happens at the end of each round. So in doing so, what we can do is this method can be coupled with low-cost online experiments like MTurk, because we can collect the data from online experiment and then run the criteria after collecting the data, and then try to figure out like the number of profiles for the second round of experiment, and then show that on MTurk, and then it doesn't require real-time update.
Cool.
So it could be coupled with low-cost experimental methods.
Cool.
Yep.
Thank you.
You're welcome. All right. So so after running the experiment with the manufacturer, we found that it is very difficult to figure out what is the best performing design profile without considering combinatorial effects. So with only main effects, we found that lots of combinations, lots of design profiles presented as tie. And then when we incorporated interactive effects, then we could uniquely identify the best performing design profile at the market level. And we also, so basically our goal is to directly test important interaction effects as much as possible by showing the right combination to the subjects. However, the criterion itself is presented as upper tail integration. So we wanted to see whether our experimental criterion did what we expected. So we counted the frequency of testing of the important interaction effects that showed up in the predicted best profile, so 3 interactive effects. And then we wanted to see whether actually those important interactive effects are tested more frequently in the subsequent round of experiments. And the red dotted line presents frequency that is coming from random draw. So if you just randomly allocate your experimental resources to your subjects, and then each interaction effect should show to be equivalent to the frequency of testing of each interaction effects should be equivalent to red dotted line. However, as you can see in the excuse me, as you can see in the figure, the important interactive effects are more frequently tested than the expected frequency after we apply the experimental criterion that we propose. But this is only internal consistency, so that means we applied our own criterion, and then we found the best performing design profile based on our method, and then the criterion actually tested the interaction effects that was presented in the best performing design profile that we predicted. So that does not mean that the design profile that we predicted is actually the best design profile. So we wanted to obtain external validity of our method. So we conducted a separate experiment, which can be viewed as a beauty contest. The collaborating manufacturer actually ran 3 additional experimentation with 3 different methods. So one was a Nielsen optimizer using the descriptive genetic algorithm, and another one is traditional sawtooth choice-based conjoint analysis, and the third one is a machine learning method, which is called the Bayesian optimal recommendation set. That is typical recommender system that was published in 2010 in the Machine Learning Journal. And there was ours. So there were actually 4 different design profiles proposed by each method, and all 4 design profiles proposed by each method were different from each other. We conducted another separate survey. So we showed these 4 design profiles proposed by each method as the best design profile. And then we included another option that I don't like any of these. So this beauty contest experiment only included 1 question. So we showed 4 design profiles and then no choice option. And then about 500 respondents from US and UK responded to this question. And then the result was favorable to our proposed design. So out of 523 respondents, almost 27% of respondents said that they preferred our proposed design. And this was actually 8% higher than genetic algorithm and 14% higher than standard choice-based conjoint, and 52% higher than optimal recommender system. And then no choice was only 7%. So the 8% is a seemingly small difference, and it is true out of 500 people. However, this product category is over 1 billion sales. So considering the 8% on the market, this is actually not a small difference. In addition, the Nielsen optimizer is a very high-cost method. It requires individual level update. So they need to hire the panel for the experiment, and they have to keep those panelists throughout the experimental procedure. So we thought that this aggregate experiment can perform better, or if not better, as good as existing commercial methods. And especially cost reduction wise, this presents a very good opportunity for firms that are interested in this class of problems. Okay, so we proposed a new statistical method to optimize a visual design with high dimensionality. And then we believe that this contributes to the literature and practice by combining preference elicitation method and goal maximization at the same time. And then we showed that it is a very efficient method to figure out the most promising design profile given limited experimental resources. And it also enhances the prediction accuracy of the best performing outcome, especially at the market level. Again, this is computationally very simple, and this does not require real-time update, so you don't need any special technology. So you can just combine them with a low-cost online survey like a Google survey or mTurk, and then you can just collect the data and then calculate the criterion in the back office. It is a very general problem, so you can apply this method to general optimization problem, especially with horizontal variation, because horizontal variation would cause higher dimensionality because of discreteness of attributes. And we believe that our experimental goal function that focuses on the upper tail of distribution is consistent with marketer's goal by focusing on the best performing part of the attribute or consumers instead of focusing on the average performance, because that would summarize the opportunity to do better than what we have done so far. This concludes my presentation, and thanks for your attention and listening to my presentation. And well, if you have any questions, further questions, you can email me, and I can share the code for this methodology, and I can share the manuscript of our research. So if you need anything, please email me at mingyuj@ucr.edu. And thanks again for your attention. Thank you.
Hey, Max, you type your email?
Sure. Let me, okay, so just a sec.
If you have any question right now, who are watching right now, if you have any question, just let me know.
Okay, so I think everybody can see.
Yeah, it has a time lag actually when we broadcasting here versus when people see that.
Oh, okay, okay.
It's not really real time.
I see.
You should be able to see Max's email now. And also, do you use R to implement everything? Do you have an R package that can?
So the project is just out. So it is just accepted at Management Science. So we didn't have a chance to wrap up as a package. However, I have a R code. I did everything in R. So everything is available in R. So if you use R, you don't need to do anything. You can just copy my code and then implement the method.
And do you have the R code somewhere, GitHub somewhere?
So at this moment, I prefer to share like by request.
Okay.
But in the future, I'm preparing for some package or some like better way of sharing. But at this moment, I'm sending it over emails.
Yeah, I think this is a very good, important topic in industry too. Like we need to do a lot of different kind of design. And there was just a paper about p-hacking. When they do the experimental design, they start to change different design and they stop at the time they find a significant p-value.
Okay.
Oh, someone asked, have you submitted a patent application?
No.
No.
No, not at this moment.
Yeah. Yeah, someone say they want to see the code. So maybe you should email Max if you want to know get the code.
Please.
Yeah. Any other question in the audience? I don't see new question coming in.
Okay.
All right. Thank you very much, Max.
Thank you very much, Hui.
Yeah.
Thank you.
Bye.
Bye-bye.